Hi everyone, and welcome to this new class in engine propulsion and specifically the design of turbines and the nozzle. So let's begin by doing a little overview of what the turbine does. So turbines, what they do is decrease the pressure, okay? So expand the flow, which means the same as decreasing the pressure, in order to accelerate the flow to higher velocities. So the turbine basically converts pressure to velocity. Using Bernoulli equation, you can see that the pressure is always related to velocity, and if we have high pressure, it means low velocity, and low pressure, it means high velocity. So a way to increasing the velocity of ejection of our fluid, what we need to do is decrease the pressure. Okay, so the flow going through the turbine has also a high temperature. And this is due to the reaction in the combustion chamber, which has taken part, between the compression zone and the turbine. So when the flow arrives to the turbine, it is actually high temperature, due to the combustion chamber, and high pressure due to the compressor, right? It's also interesting to note that one of the main objectives of the turbine is not only to accelerate the flow, but actually to provide rotation through the shaft to the compressor. And by providing this rotation to the compressor will be able to pressurize the fluid and therefore reacting correctly in the combustion chamber and optimizing the complete engine cycle. Now, an overview of the nozzles is pretty straightforward. The idea of a nozzle is that the flow is furthermore accelerated. It's not only accelerated due to the turbine, but also accelerated a bit more due to simple geometry. By using a conversion nozzle in case of a subsonic flight. So you can see that this is just a graph that I found. It's quite intuitive. You have a velocity a mass flow going at this velocity, and due to the conservation of the mass flow, we will have higher velocities just because the total area is decreased. So we will have an increase of the velocity due to geometric constraints. That's all. So you can see a bit of the nozzle. It doesn't have the idea is that you cannot do it too much because of the properties, the energy properties and kinetic properties of the gas, but you can actually provide a bit more velocity due to a converging nozzle. As before, as happened in the same case as the nozzle, there's no difference of pressure on the fluid, due to the nozzle. So it is simply a way to accelerate the flow with no difference of pressure. One topic that I wanted to discuss also are the afterburners, which some of you may know from aircraft, specifically mostly from military aircraft, which is kind of interesting to know that you can actually provide an additional propellant, so an additional burning part of you can actually provide more energy to the fluid by burning the fluid at the nozzle, and this is actually known as afterburner. So my definition would be that some aircraft introduce additional propellants, so that the flow at the nozzle is burnt again. And this, what actually does, as you can see, is create this kind of interesting, fact that some of the fluid is seen as if it were burnt, or afterburnt, and it's, you've probably seen it for supersonic flight. And these kind of afterburners are quite usual in supersonic aircraft, and what they do is provide additional thrust. However, the main drawback is fuel efficiency, because you're basically burning more fuel in order to get a bit more thrust. In general terms, you won't find this in commercial aircraft. It could be done, but it's not efficient. It's not fuel efficient, And so this is not the case unless we need extra thrust or we need very high thrust, which is what usually happens for supersonic aircraft. Okay, so I think we can go to the next topic.